Okay, continuing on with chapter 16, the different combinatorial and parallel synthesis techniques. We talked about briefly solid phase organic synthesis, and the S here is solid organic synthesis. And we talked about the different resins. I wanted to also point out why is this a great technique to carry out the reactions? Well, several reactions can happen at the same time. So you can do these in the different wells. So a lot of times you'll have reaction wells. So you'll have a little reaction thing and you can have the different reaction wells. And these are little containers and you put different reagents in each one of these and the reaction takes place in those wells. Okay. Um, Now the advantages are you can you'll have your material, your starting material of your reaction bound to a resin. And then you can add excess reagents which will drive your reaction to completion, and then you can just wash away the unreacted reagents or any kind of impurities. You just use a solvent that is that will rinse away the unreacted excess reagents. This is nice because a lot of times it can drive your reaction to completion. Another thing is you don't have to purify, you're not purifying each intermediate. When you do solution phase chemistry, you have to isolate and use chromatography to purify each intermediate, but here you just keep growing on the resin and you do a wash. So they don't have to be purified, and you can also regenerate your resin. So you can do different starting materials on the different beads in case you're doing combinatorial chemistry. Now the essential requirements for solid phase chemistry is you have to think about your resin bead and the synthetic conditions, because when you're doing your chemistry reaction, if you're like in your Merrifield resin here and you have an ester, that gets cleaved under acidic conditions. So you've got to be considering when you're doing your design of what functional groups that you're going to be synthesizing and changing, that you don't want to cleave off your compound from the resin. Another thing you have to always consider is protecting group. Okay, so protecting groups are important when you're thinking about the resin. So this is actually slide 18, the different protecting groups in your PowerPoint slides. So I would refer to those as you're taking notes and reading this chapter. But the typical ones you have are like the Bach, the benzyl. Okay, so a benzyl group is like this. A Bach group is like this. For the nitrogen, you have the F-MOC group, which looks like this. And then the other one you have is the tert-butyl, which protects alcohols. And so the tert-butyl that protects. So what is that functional group that these protects? The Bach will protect an amine. The benzyl will protect alcohols. The F-MOC will protect amines. And tert-butyl will protect alcohols. So what does that look like? This will be attached to the nitrogen here. You can imagine that's a carbamate functional group. You don't usually learn that. Benzyl right here, and then this would be a carbamate right here. Okay, and so these are cleaved in trifluoroacetic acid, CF3OH, trifluoroacetic acid. Benzyls are cleaved in hydrofluoric acid. They're actually stable in TFA, so that is a combination because you can work off of a benzyl resin and you can protect your amines with a Bach group, and then you can cleave those off with TFA, but yet you still have your material bound to your resin because you don't have to cleave it until you use HF. FMOC group is cleaved by piperidine. So this is a organic base, it's not acid. And then tert-butyl is cleaved by TFA, and so it's stable to piperidine. So a lot of times you'll use this as a combination so you can deprotect your nitrogens, your amines, using a basic solution of piperidine, and then that does not cleave your chain or your starting material from the resin, and then you can cleave from the resin using TFA. So that is the protecting group strategy for the resins when you're designing your different chemistries. Okay, so we also talked about the differences between parallel synthesis and combinatorial chemistry, and the biggest difference is, and let's look at an example. The biggest difference is in parallel chemistry, you're going after a certain number of compounds. So let's look at something like this. So if you wanted to do a parallel synthesis, let's do reductive amination. Okay, so you have an aldehyde, and it reacts with an amine. Okay, you're going to react that to make an imine, and then you're going to throw in some sodium cyanoborohydride to reduce it to make your amide. And so you'll make a new amide. So maybe you pick 3 different aldehydes. Okay, so you pick these 3 different aldehydes, and you have your wells here, and we're going to react them with 3 different amines. Okay, so we have these 3 different amines. So you can, this one will react with 1, 2, 3. So if you put that one there, you put this aldehyde in these, 1, 2, 3, and then you put this aldehyde in here, 1, 2, 3, then you can put the other amine here. Let's see, we can put this amine in this one. Actually, you would want to put them going down, wouldn't you? Okay, so if you put the blue aldehyde going across and the red, then you would put the green going down. If you wanted this one to be blue, the amine, and then this one here. And then so each one of these gets to react with each one of these amines. This reacts with that amine. And so let's just look at a product you would get from the first one. It would make the amine like that. That's your amine. And then it would reduce this to the oh, actually, we're just making amines here. Not amides. All right. Okay. And then that would get reduced, and you'd make that amine in this well here. And then the next one, where you added this one here, you would get this compound, right? That would be that secondary amine. And then in this one, you would get that compound. And so you would know, you could tell, but because you would keep track of what you're putting in each one of these wells, you would know what reaction, and you'd know the identity in that well. And so you can see that if you have 3 aldehydes and 3 amines, you would get 3 times 3, you would get 9 different products. And then those compounds you would purify. And what kind of techniques would you use? A lot of times you would, a lot of times people use microwaves to get the reactions to work faster. You use a thing called solid phase extraction. And that's in figure 16.15. So if you look at that, that's a solid phase extraction, SPE, and we did this a lot. So you see those. This is instead of separatory funnels. Okay, so a lot of times you all have used separatory funnels to separate the two liquids, right? And you have the more dense liquid here, and then you have the less dense liquid here, and that might be aqueous, and this might be dichloromethane. And solid phase, you basically will remove acidic or basic compounds of their impurities. You could have the different, you have a pipetter. So if you can see that thing, you have a thing that actually, you'll have your wells. Okay, because you got to imagine this is on a plate. Okay, and then you have this solid phase extractor, and it'll go down and it will vacuum up the solution phase. And that's how you can rinse this. We use a lot of these SCX columns and SAX columns. So the acidic columns were the SCX columns, and the basic columns were the SAX columns. These are really nice. So basically, you can put your solution onto the column, and it will bind, and then you can wash with different solvents. And so you can imagine you would have all of these, and you would literally have a rack, and you would set up all these columns here. And you had this like handheld device that you could literally crank down. So you could just put your solutions in, you could crank this thing down, and then you'd have your well plates here. So everything you do in your organic chemistry laboratory now, you do it, but you do it when you do that one thing, you do it one time, and you're getting 9 products. So those are a big deal, the solid phase extraction and the different columns. Another thing you have is a thing called reagents are attached to solid support. Okay, so a lot of times, like if you wanted, you can get sodium borohydride resin. Okay, and you know, like with the reductive amination reaction that we just looked at, if you needed to do a reduction, so let's say we were making this compound here and we had the amine, right? So we made this, and then we need to react it with sodium borohydride to reduce the amine. What you can do is you can add this resin-bound sodium borohydride, and then you've got this, you have a solid, this would be a solid precipitate, and you can just do a filtration, and you have your amine in the solution phase. So a lot of resin bound. You can also do a thing called catch and release. So these are reagents attached to resins, to solid supports. You can do a catch and release, and that means you can do your reaction. So you have a starting material here, and you can have the reagent here. So I'm thinking of how about an amide bond using DCC, and so you can take your starting material, and this will make it an activated ester. Okay, so if you have an ester here, or I'm sorry, a carboxylic acid, if you have carboxylic acid and you have DCC, okay, DCC would catch your carboxylic acid, and DCC would form some kind of catch, and then you do your reaction, and then you could rinse it with, in this case, probably an amine, and then all of a sudden your product is kind of happening, the reaction is happening on this resin, and then it releases it to give you your product. So you want to do a lot of resin bounds because that way you can just do a rinse and separate. Now let's talk about the difference between combinatorial chemistry. I don't think of combinatorial chemistry synthesis, it's messy, you know, it's not quality. The parallel synthesis is quality. I mean, you want your reactions to go well, you know exactly in each well what compound you're making. Here you're using a mix and split method. Okay, so, and I'm just going to refer you to the slides because they show a really nice example in your slides of the mix and split method. But you might be taking like, and it's also in figure 16.29 on page 341. And you can see, like, if you're making different amide bonds and you react with glycine, alanine, phenylalanine, valine, serine, and you have everything resin bound, and then you can mix them all up, and then you split them, and then you react them again, and you mix, this makes a tripeptide. So, and then in each well, you don't even know what you have in those wells. A lot of times what you want to do, your whole goal is to make a big, huge compound library. And you can use a lot of the computer techniques to do this as well. A lot of times in order, the whole goal then is what do you have in your well? And when do you care? You only care if it's active. So, and you have to have an active compound. So a lot of times what you'll want to do is you'll actually want to put your target in the well. And then if it shows activity, then that is a well you're interested in. And then the goal is to go back and figure out to identify the compound. So there's some sophisticated methods to do this, to find out the determination of that active compound. And you see them on page 341, tagging, okay? Tagging and barcoding. And so what you do a lot of times is on your resin, you will have something on that resin that can have a certain retention time. Okay, and so then you can do different like HPLC, GC, different like the gas chromatogram that you see on figure 1632, and based on the retention times, you can identify what your compound is. So you want to tag that so then you can be able to isolate it. Dynamic combinatorial chemistry is where you're actually screening compounds with the target, but keep in mind your target has to be stable to the solutions and the reactions. So on paper it sounds nice. In reality, it is so messy. But you're dealing with just big compound libraries in order to get active compounds and lead compounds. And you can imagine, let's go back to thinking about the infectious disease. 6 years, no lead compounds. So you would take a compound library of 1,000 compounds, and if you could get 5 active wells, okay, that show some kind of interaction in one of these wells, then you would gladly try to figure out what is in that well, okay? And then once you figure out what that compound structure is, then you can go back and use your traditional synthetic methods and stuff like parallel synthesis to do the different structure-activity relationship changes, kind of the reactions that you proposed last chapter, okay? So these are tools in order to make finding that lead compound more efficient and doing lead optimization.